Good afternoon to all. So this is our 22nd lecture. Till now we have tried the applications of Reynolds transport theorem for three different properties. The first one was mass, second was linear momentum, and third was angular momentum. Okay. So the application of angular momentum one, what I will do, if time permits, then today I will discuss one numerical problem after this. Otherwise, I will discuss it in the tomorrow's lecture. Okay. So now the next important property, which is of relevance for fluid mechanics analysis, is actually energy. Okay. And while we will be discussing the concept of energy, you will be finding that it is having direct connection with the subject of thermodynamics. Okay. So to much extent, we don't use energy equation in the course of fluid mechanics for the fundamental aspects, but whenever we go to the applied part, okay, applied portion of the subject, for example, whenever we will be discussing the fluid machines, particularly the turbines, pumps, and other devices, there comes the applications of energy. Okay, so whenever we have to start the energy equation and we have to write it for a fluid dynamic system, we have to start with the fundamental definition of the energy or the fundamental energy conservation principle. Okay, so if you see from the subject of thermodynamics, the fundamental energy conservation principle is nothing but our first law of thermodynamics. Okay. So as per the first law of thermodynamics, we all know that for a system, del Q minus del W is equal to dE. So this dE, whenever I am writing, this is applicable nothing but for a system. Okay, so that is something which we already know. For a closed system, for a control mass system, we will be having delta Q minus delta W equal to dE, where this Q represents the heat transfer, okay, W represents the work transfer, okay, and E represents the total energy of the system. Okay, and whenever we are talking about the fluid mechanics, so whatever our system is nothing but a fluid mass. So our fluid mass will be acting as a system. Okay, so now whenever we will be dealing with the subject of fluid mechanics, of course we are talking about the motions of the fluid. So that's why I will be defining this first law of thermodynamics in particularly the rate form. Okay, so if I have to write this equation in rate form, it will become del Q by del T minus del W by del T equal to dE by dt for the system. Okay, and now you must be very clear that why I am writing this term as del Q. Can you tell me why I am not writing it exact differential D, why I am writing it delta? Because you have already studied the subject of thermodynamics now, this concept. Why I am using del operator over here instead of delta, D? Yeah, so this is nothing but a inexact differential. So for inexact differential, I am using this delta symbol, and D is for actually the exact differentials. Okay, so now ultimately, if you see, this right hand side is nothing but applicable for a system approach. Okay, now I have to convert this to a control volume approach. So if I have to convert this quantity into a control volume approach, what I have to do? I have to apply the Reynolds transport theorem over here. Okay, so we know that in the Reynolds transport theorem, while I have discussed that concept, I have taken any generic property B. So B over here will be nothing but equal to energy. Okay, and if I define the intensive property beta, which is B per unit mass, that is coming out to be here nothing but say small e. Okay, and what is small e over here? Small e over here, please tell me what will be small e? From the subject of thermodynamics, tell me. Half V square plus GZ. Okay. Anything else? Sorry? P by rho. Okay. What does E represents? E represents the total energy. So that is the sum of microscopic energies plus macroscopic energies. So I have discussed the microscopic energies as half V square and Gz. These are nothing but the kinetic and the potential energies. Other than these, internal energy, the microscopic energies are nothing but constituted inside a single term which is called as internal energy, U. Okay. And while we are discussing about the internal energy, here we are considering only the inter and intramolecular interactions. Okay. And when I will be having any sort of chemical reactions or nuclear reactions, these are also not accounted in this internal energy. Okay. So if I have to account for the chemical interactions, chemical reactions, nuclear reactions, so then I have to use some additional other energy which will be accounting for other interactions such as chemical / nuclear. So this is one very important point. Whatever the thermodynamic state you see in your properties of pure substance or the steam tables, okay, or other property tables for different substances, these property tables nothing but include only this internal energy which is not having any contribution of chemical reactions and nuclear energy. Okay, so chemical reactions and nuclear energy comes into picture when we talk about particularly the subject of chemical thermodynamics. Whenever we study the engineering thermodynamics for mechanical engineering student, there we don't consider this term. So typically we say that in our system which is under consideration, fluid is not undergoing through any chemical reactions and it is not going through the nuclear reactions, then this we will be considering equal to 0. Okay. Now you must be able to answer it very easily because you have already studied this in thermodynamics. Okay. Okay, so now what I will do, I will try to write this equation again. So I can write left hand side as del q by del t minus del w by del t, and can you tell me now what will be d by dt system? In control volume approach, it will be nothing but d by dt of integral over the control volume small e times rho dv bar plus integral over the control surface e rho v vector dot n cap into d. Okay. So this is nothing but I can say the first law of thermodynamics for a control volume system, open system. Okay, so this is nothing but over here complete analogy is from the subject of thermodynamics. Okay. So now I have to define different quantities over here. So typically when we talk about the heat transfer, so you can see that from our fundamental understanding, depending upon what type of mechanism is actually participating in the heat transfer process, we can have conduction heat transfer, we can have convection heat transfer, or we can have radiation heat transfer, but we are not interested in at the moment in analyzing that what mode of heat transfer is taking place, and in majority of the cases for the subject of fluid mechanics we will be even neglecting heat transfer to be zero. Okay, then next part come, we have now other quantity work. Okay, so can you tell me what are the different possibilities for work we will be having? So one will be work because of the surface forces. So what are the surface forces involved in our system? So surface forces involved in our system are pressure force. So one will be work because of pressure force. Okay. So this I can simply say that as say pressure work. Then I will be having another surface force involved which is nothing but the viscous dissipation. So I can say that work because of, particularly because of the shear stresses which are coming because of the viscosity. Okay. So I can call this as work because of the viscous effects. Okay. And if I have a closed mass system, then I have displacement work also. But over here, whenever we will be talking about the fluid dynamics approach, we are always referring to a control volume approach, which is nothing but of fixed size. Okay. So there another important work will be coming into picture, which typically we call as nothing but our WS, and in other words I will be calling it as shaft work. Okay. So what do we mean by shaft work? Any work which is taking place through the boundary of the control surface, okay, and that energy interaction is not because of the temperature difference and neither because of the pressure and viscous dissipation. So that we will be calling as soft work. For example, if you talk about a fluid machinery, then when impeller of a centrifugal pump is rotating, it is imparting certain amount of energy to the fluid medium which is adjacent to it. So that is nothing but imparting in the form of a soft work. If you have a fluid is flowing over the impeller of a turbine, then you will be finding that that turbine is actually producing some amount of work output because of the fluid interaction. So ultimately that work output can be seen in terms of the rotation of a shaft. So that's why we call that as nothing but a shaft work. Okay. So these are the different amounts of different interactions of work which will be involved in our system. So now one by one let's try to define these. So of course whenever we are talking about the shaft work, I cannot generalize it. It will be simply if we are able to measure the torque and rotational speed of the shaft, then I can define this as shaft work as nothing but torque times omega. Okay, so that will be my shaft work. But ultimately, now the other important work comes from the perspective of the fluid mechanics, that is nothing but our pressure work. Okay, so of course, what will be pressure work which is acting on a small fluid element dWp. So it is in the rate form dW dot P. So wherever I am putting dot, the meaning of dot is I am doing d by dt. Okay, so I am writing it in the rate form. Okay, so when I will be talking about the work, then dW dot P will be equal to, can you tell me what will be the formulation of pressure work? It will be nothing but pressure force acting on any elemental area dA. So what is pressure force acting on elemental area dA? Minus P into dA. Okay, and then we have to also, this is the force. If I have to find out rate of work done, then I have to multiply this with the work, with velocity. Okay, force times velocity will be giving me the rate of work done. So I have to consider that if this is my boundary of the control surface having elemental area dA, then whatever the inward velocity of fluid is there at this boundary, that particular velocity will give me nothing but my work when it is multiplied with the pressure force. Okay, so I will be consider over here inward velocity. That's why I am using minus v vector dot n cap, because that velocity has to be normal to the interface. Why? Because work is acting normal to the this pressure force is acting normal to the interface. Yes, inward. Yes, inward velocity of the fluid which is just passing the control point. Okay. So this is, and in other sense, you can call this as nothing but your flow work. Whenever you discuss the subject of thermodynamics, then we call the work as nothing but the flow work, product of pressure into volumetric flow rate. Okay, and specific flow work is nothing but product of pressure into velocity. So ultimately, what I will be finding from here is that if I have to find out total pressure work Wp, then of course I have to integrate this over the entire control surface, and that will be becoming minus P minus V vector dot n cap into dA, and ultimately I will be getting integral over the control surface P into V vector dot n cap dA. Okay, so this is my pressure work. Okay. So similarly, I can have another work which is called as shear stress work or viscous work. Okay. So viscous work will be in the similar fashion, Wv equal to integration over the control surface. Now, what will be viscous force? If tau is the viscous stress, then viscous force will be tau times dA. So minus tau times dA is the viscous force, and this has also to be multiplied with velocity, so v vector. So ultimately I will be getting minus integral over the control surface minus tau times velocity vector, tau dot velocity vector into dA. Okay, so this is my viscous work. This point is clear? Sorry? No, here only velocity is v vector, not minus v vector. Sorry, I have to put only symbol. Yes. Okay, so this is tau dot v vector times d. Okay, now one important point is that if I am calculating the viscous work at a solid boundary, say if I calculate it for a solid boundary, what will be velocity at a solid boundary? Because of the no slip condition, it will be 0. So ultimately value of viscous work will be coming for a solid boundary to be 0. Okay, if I calculate viscous work for an inlet which is having flow normal to the inlet.
Tau is stress, right?
Yes.
Stress is not a vector, so you cannot take a dot product of
It is a tensor quantity. Stress is a second order tensor. Okay, so we will discuss about this second order tensor in more detail in subsequent lectures. Okay, so it's a tensor quantity, that's why you can do it. Have you attended kinematics part, shear strain when we have estimated? So strain was a tensor, second order tensor. So when it will be multiplied with viscosity, that will become nothing but a stress, viscous stress. Okay, so that's why this is also a tensor quantity. Okay, so now what we have to do is, say this is my inlet, and this inlet is designed in such a way so that the flow is always normal to this inlet. So if flow is always normal to this inlet, so whenever I'll be talking about this particular inlet, so at this inlet I have to consider for the inlet work only the stress tensor, the component of the stress tensor which is parallel to this velocity. Okay, so parallel to this velocity stress tensor component will be nothing but normal viscous stress. What I will be having? Normal viscous stress. So we have shear viscous stress, similarly we have normal viscous stress also. Okay, so the normal component of the viscous stress is usually of very small magnitude. So this is usually of very small magnitude. As it is of very small magnitude, that's why whenever this normal component will be multiplied to our inlets or outlets where flow is perfectly normal to the plane of that particular inlet or outlet, under that scenario also I can define that my viscous work for inlets / outlets which are having normal flow, there it will be equal to 0, nearly equal to 0. Why I am putting nearly equal to sign? Because our normal shear stress is not exactly equal to 0, but it is nearly equal to 0. Okay, this point is clear. So how it is nearly equal to 0? Subsequently, whenever we will be discussing all the components of the viscous viscous stress tensor, then we will be able to define these different parameters. Okay, point is clear? So there also work will be nearly equal to 0. Then ultimately we also know that if I consider, say, my boundary layer, so in this boundary layer, say this is my boundary layer region. Now all of you must know what I mean by boundary layer, because I have already described briefly in the earlier lectures. Okay, so if I consider any streamline over here and if I consider another streamline over here, can you tell me along which streamline my viscous work will be non-zero and along which streamline viscous work will be zero? So outside this boundary layer viscous effects are gone. I will be having velocity as completely uniform along this streamline. So there will not be any velocity gradient along this streamline. So if there is no velocity gradient, there is no strain. So viscosity times, coefficient of viscosity times strain rate forms viscous stress, and that will be equal to 0 outside. So that's why W viscous will be 0 over here. Whereas if I talk about this particular point, so here I have some gradient of the velocity existing along this streamline. So that's why Here I will be having a non-zero viscous work.
Why does outside boundary layer we do not have any velocity gradient?
Outside boundary layer, because we have moved significantly away from the solid surface where effect of viscosity can be felt. Okay, so it's a simple case. Aeroplane is moving, so influence of the aeroplane can be felt up to certain distance towards the ground. But if you go exactly at the surface of the ground and the aeroplane is going at say few thousand meters above the surface, then you will be feeling far away from that effect of that particular flow is not felt actually. So similar situation. Point is clear? Okay, so now yeah, we have had enough discussion on different components of the work. Now let's try to club together these works into our generic equation. So if I do so, then I will be finding that my generic equation, yeah, I have to write this equation again now. So this is my generic equation, say this is equation number 1. So I am rewriting equation number 1 once again. So my equation number 1 will be Q dot minus W dot. What type of W dot we have now? W dot because of the pressure minus W dot because of the viscous minus W dot because of the shaft work, and that will be equal to d by dt of integral over the control volume E. In place of E I can write U plus half V square plus gz into rho times dV bar plus integral over the control surface U plus half V square plus gz rho times into V vector dot n cap dA. Fine. Point is clear? One important point which particularly we take from the thermodynamics, because while I have taken this equation del Q by T minus del W by T equal to dE by dt, it is coming from thermodynamics. So there two sign conventions we have assumed is that the first one is any heat added to the system means which is entering into the system, entering into the control volume through its boundaries, that is taken as positive, any heat which is going out is taken as negative, and opposite is true for the work interactions. So work interaction done by a system means going out of the system is actually positive and entering into the system is negative. So this is the convention which is already included in the main equation which I have started. Okay. So now let's substitute different work formulations over here. So if I substitute over here, I will be getting Q dot minus integral over the control surface P into V vector dot n cap dA minus minus will become plus integral over the control surface tau dot V vector dA and minus W dot shaft work, and this will be equal to the right hand side which is remaining as it is, so I am putting just an arrow. Okay, is this point clear? Now what will be happening? If you see here, I have on the right hand side integral over the control surface, here also I have integral over the control surface. Okay, so I can club together these two integrals into the single one. Okay, so if I club together these two, then ultimately what I will be getting? Ultimately I will be getting Q dot minus integral over control surface tau dot V vector dA minus W dot S equal to d by dt of integral over the control volume U plus V square by 2 plus gz into rho dV bar plus integral over the control surface U plus, now this P will go to the other hand side and it will become a positive sign, and if I take this rho common out of the P also, so it will become U plus P by rho. Okay, plus V square by 2 plus gz times rho into V vector dot n cap dA. Point is clear? Okay. What is this quantity now? U plus P by rho. Enthalpy. Okay, so this quantity is nothing but from the subject of fundamental thermodynamics, we call it as enthalpy. Okay, so ultimately I can write that Q dot minus, let me write this as viscous work only, because at the moment we don't have idea about the shear stress tensor, so that's why we are not going to calculate it. So I am writing it in the generic form as W dot V minus W dot S, sorry.
Plus viscous force. Never.
Here, what I have missed?
Minus became plus, right? Control. That term became plus.
Oh, sorry, yes, plus. So when I am using this formulation tau, then it is becoming plus, but if I am writing simply viscous work, then it is coming as a minus sign, because that is minus of that. Okay. So this will be equal to d by dt of integral over control volume u plus v square by 2 plus gz into rho dv bar, okay, plus integral over control surface h plus v square by 2 plus gz into rho v vector dot n cap dA. Okay, so this is nothing but my generalized energy equation. So this is generalized energy equation for any type of flow. Okay, so for any type of flow, if I am analyzing using a control volume approach, then I can apply this particular equation. Fine. So one important point you must notice is that how powerful is Reynolds transport theorem. Okay, so anything you know for a system level approach, by just knowing the correct application of Reynolds transport theorem, you can apply it to the other approach. Okay, so that is the actually power of Reynolds transport theorem. So that's why it is necessary for everyone who is engaged in the course of fluid mechanics to know the correct use of Reynolds transport theorem. Okay, because it is helping us in many ways. So whatever the things I am doing over here with the application of Reynolds transport theorem, same things can be done by applying the first principle, like using a control volume and then considering different energy interactions. By that approach also this can be done, but then it will be becoming a more lengthier procedure. Okay, so this RTT is helping us in actually doing it very swiftly. Okay, so next now let's try to invoke certain assumptions. The first assumption which we will invoke is steady flow. All of you know, I need not to explain what is steady flow. I think in thermodynamics many times you have studied in even more detail. Then second assumption which we will invoke is 1D inlets and outlets. What is the meaning of 1D inlets and outlets? I have explained you before also, I am writing it again. Uniform properties across cross section. So that is the meaning of it. Fine. So now if I do invoke these assumptions, then ultimately this first term will be becoming, once I invoke the steady assumption, this first term becomes 0. Okay, and now this integral over the control surface can be converted into a summation sign. Okay, and this product of rho v vector dot n cap into dA will be becoming nothing but my mass flow rate approach. Fine. So ultimately what I can do after I invoke these 2-3 assumptions, I will be getting that Q dot minus W dot V minus W dot S is equal to summation H plus V square by 2 plus GZ for outlet into mass flow rate at the outlets minus summation of H plus V square by 2 plus Gz for inlets into m dot at the inlet. Fine. So we have nothing but got a simple algebraic equation. And this equation is nothing but the one which you study in your subject of thermodynamics applied to a open system or a control volume. Okay. And I will be calling this particular equation as nothing but steady flow energy equation. So most famously it is known as steady flow energy equation. Okay. All are clear with this? Now let's consider that we have only single inlet which is designated by point number 1, and I have a single outlet which is designated by point number 2. So then this summation will also go away and I can simply write as 1 into. So ultimately what I will be finding is that if I try to find this steady flow energy equation for single inlet and single outlet control volume, then I will be getting that Q dot minus W dot V minus W dot S equal to H1 plus, H2 plus V2 square by 2 plus GZ2 into M dot 2 minus M dot 1 into H1 plus V1 square by 2 plus GZ. Okay. Now one important point, if I have only a single inlet and single outlet for a control volume and I am saying that it is nothing but a steady flow system, so then M dot 1 must be equal to M dot 2 and which will be equal to some mass flow rate M dot. Fine. Today whatever we are doing is nothing but just revision of thermodynamics, what you have already studied. So I think in thermodynamics this topic is already studied because you started now, I think second law. So we will be now, what we will be doing, we will be dividing this entire equation, the first one by m dot. So if I do so, I will be getting small q dot minus small w v dot minus small w s dot, where q dot is nothing but capital Q dot by m dot, w v dot is nothing but, small w v dot is nothing but capital W dot v by m dot. Similarly for shaft work also I can write that small ws dot is nothing but capital Ws dot by m dot. Okay, so this is on per unit mass flow rate basis and ultimately this will be coming equal to H2 plus V2 square by 2 plus GZ2 minus GZ. Okay, this point is clear. So now what I will do, I will once again play with this equation. I will divide this equation throughout by G and also I will write this enthalpy term separately as internal energy plus flow. Okay. So if I do so, then I will be getting Q dot by G minus W dot V by G minus W dot S by G equal to, in place of H2 I will be having P2 by rho G plus V2. So right now it is rho 2G. Okay. V2 square by 2G plus Z2 plus U2 by G. Fine. And minus of P1 by rho 1G Fine. Now, what is the benefit of this equation? The benefit of the equation is that if you see the dimension of all the individual quantities, this has to be dimensionally homogeneous. So Z is nothing but representing a length dimension. So this length dimension is called as head. So here I will be calling this as potential head. This I will be calling as kinetic head. This I will be calling as pressure head. Similarly, these will be nothing but heads of heat and work. Okay, so now this equation is written in terms of head. So this particularly the head notation, okay, or the representation of this steady flow energy equation in head form is mainly used by basically the civil engineers. Mechanical engineers are more interested in the energy concept, but majority of the time for analyzing our flow situations in fluid mechanics, particularly flow through the conduits, closed vessels as well as the open channels, we also use the approach of this steady flow energy equation in head form. Okay, and another reason for discussing this equation in head form is that you will be finding some close similarity of this equation with another famous equation which is called as Bernoulli equation. Okay, so this equation will give close connection, close comparison with the Bernoulli equation. So that's why we are trying to study this in the head form. Okay, so now it is if I ask you Bernoulli equation, I think all of you will be telling me. Tell me, what are the different terms involved in Bernoulli's equation? Pressure head P by rho g plus kinetic head V square by 2g plus potential head Z. Okay. So, are you finding some similarity of this equation with the Bernoulli equation? So, some similarity you can see over here. So, now what I will do, I will try to segregate it in a similar fashion. So, if I do so, I can write it as P2 minus P1 by rho g plus V2 square minus V1 square by 2g plus Z2 minus Z1 equal to Q dot by G minus W dot V by G minus W dot S by G and minus of U2 minus U1 by G. What is clear? So now left hand side is nothing but exactly identical to your Bernoulli's equation. But in the right hand side there are some additional terms. Okay. So the additional terms are nothing but one we have is head because of heat. Then these two are heads because of work, and third one is head because of change in property of the fluid. Okay, so internal energy is nothing but representing the changes in the properties of the fluid medium by changes in fundamental properties. Okay, so that is something which we have seen over here. So ultimately, what I can say is that this left hand side can be simply equated to some heads. So if I simply consider that, what is this P2 minus P1 by rho g? This is the difference of pressure head between outlet and inlet. This is difference of velocity head and potential heads between outlet and inlet. Now if I consider between outlet and inlet, I have a long pipe. Okay, so what will be happening between inlet and outlet for a pipe? I will be having some frictional pressure drop. So I will be having some head loss because of the friction. So outlet minus inlet for a pipe flow must be equal to head loss because of friction. So this is for frictional head, typically applicable for pipe flows or flow through ducts. Okay. Then similarly, now if you consider, say you have outlet, you have inlet, and in between outlet and inlet you have connected a turbine. What that turbine will do? Turbine will extract the energy of the fluid. So as it will extract the energy of the fluid, it will give us some positive work output. So I can have some HT. This is nothing but I can call as turbine head. If I use a turbine. So I am using this as a generic form. Now all these terms are not applicable at the same time, but some of the terms will be applicable depending upon our requirements. Okay. Then similarly, if I use a pump, what pump will do? Pump will impart certain energy to the fluid. So it will impart certain head to the fluid medium. So as pump is imparting certain energy to the fluid medium, what we will be doing? We will be finding that is head supplied on the system, on the fluid medium. So if head is supplied on the fluid medium, I have to put a negative sign over here. Okay, so this is in very generic sense. If I don't want to go in very much details of all these quantities, if I consider only the physical situations which will be of relevance for us in the subject of fluid mechanics, these will be nothing but I can have a long pipe, and in the long pipe I can have frictional pressure head loss. Okay, I can have a turbine connected between inlet and outlet, which is actually extracting the energy from the fluid. So work is done on the fluid by the turbine, and I can also have a pump which is doing or supplying certain head on the fluid medium. Okay, so this is nothing but my steady flow energy equation, and the benefit of this steady flow energy equation is that you can apply this particular equation to any type of situation. This is a generic equation. The only fundamental point we have to consider over here, the two assumptions which we have invoked are steady flow and second is uniform flow. Okay, inlets and outlets are uniform. So if these two conditions are satisfied, I can apply this to any system. And this can be applied for a frictional system because it is accounting for the total energy. So that's why if in any system, if there is some frictional loss, that also can be accounted for in this particular equation. On contrary, if you talk about the Bernoulli equation, now next we will be deriving the Bernoulli equation only, but the primary nature of the Bernoulli equation is that it is applicable for a frictionless system. Okay, because all the heads at inlet and outlet we equate by considering that there is no addition or subtraction of the energy in between the inlet and outlet. So it means whenever I will be talking about the Bernoulli equation, I cannot consider any turbine or pump connected between an inlet and outlet and then I can apply Bernoulli equation. Okay, I cannot consider any frictional loss whenever I am applying Bernoulli equation. So how to do that? Let's see now next. So next is our frictionless flow. Why I am calling frictionless flow? Because I will be now discussing about the Bernoulli equation, and the key feature of the Bernoulli equation is that it is applicable for frictionless flow. Okay. So to analyze the Bernoulli equation, we will be considering that I have a stream tube. Okay, so you must know now what is a stream tube. So the collection of streamlines forming a tube surface, that is called as a stream tube. Okay, so let me consider that I have a stream tube of infinitesimally small size, and at this end of the stream tube I have density as rho, pressure as P, velocity as V, and area as A. And on the other end of the stream tube, I have density as rho plus d rho, pressure as P plus dP, area as A plus dA, and velocity as V plus dt. Okay, and as this is a stream tube, so of course all these stream tubes, if I consider that this stream tube is of infinitesimally small size, so when it is of infinitesimally small size, it will be identical to nothing but a streamline. Okay, so if I consider a stream tube which is of infinitesimally small size, that is nothing but identical to a single streamline. Okay, so let's consider that here this stream tube I have drawn along a streamline which is having surface ds. Okay, and say this is oriented at an angle theta, and with vertical distance and horizontal, say this vertical distance covered by from one end to other end is nothing but dz. Okay, so from the geometry I can say over here that dz is nothing but equal to ds times sine theta. Okay, point is clear? All are clear with this point? Now what we will do, we will try to apply the Reynolds transport theorem for mass and linear momentum, particularly along the streamline. Okay, so first let's apply the Reynolds transport theorem for mass along a streamline. Also let's consider that the volume of this stream tube is equal to dV bar. So if dV bar is the volume of stream tube, what will be its approximate value? A is area at one end and it is displacing through distance ds along the streamline. Okay, so though area is variable, but if I consider that dA is of very small size, then volume of this stream tube will be equal to nothing but A times ds. So that's why I am not putting direct equality sign over here, I am writing nearly equal. Okay, so area times distance will be my volume, and this area over here I am taking the approximation because I am neglecting the dA amount of area over here. Okay, so variation of area along the streamline I am neglecting, that's why I am writing it as nearly equal to ds. Okay, so now if I write down the RTT for mass along the stream tube direction, then what it will be? D by dt of integral over control volume rho dV bar, fine, plus control surface rho v vector dot n cap into dA equal to 0. Okay, so this is a stream tube, I am applying it along the vertical direction. So it is having some mass inflow over here, m dot in, and here it is having some mass outflow, and that outflow is say m dot plus dm dot. Okay, so that is the mass outflow. So what I can do, I can write this equation now. I will take this d by dt inside. So once I take d by dt inside, I will be getting integration over control volume del rho by del t dv bar plus m dot plus dm dot. This is the mass flow rate which is going out at this outlet, and mass flow rate which is entering is minus m dot. Fine. So this must be equal to 0. So from here, because I am doing this integration over the volume of the stream tube, so that's why this integral will form del rho by del t into dv bar only, and plus I will be getting this mm cancelled, dm dot equal to 0. So this is my conservation of mass principle along the streamline. Okay. Now next I will apply the conservation of volume principle along, conservation of linear momentum principle along the streamline. So tell me, what will be RTT along a streamline? So sum of all the forces which are acting along streamline, these must be equal to integral over the control volume del by del t rho v, velocity along the streamline is v, rho v times dv bar plus what next? Integral over the control surface into v rho v vector dot n cap into dA. Fine. So from here I can simply write that sum of the all forces will be equal to integral. I can do once again the integration. So that will be coming out to be del by del t of rho v times dv bar, because my total volume is dv bar only. Okay. And here I can simply write d of change of linear momentum. So change of linear momentum will be d of m dot into v. Okay. This point is clear. M dot into v is the linear momentum at inlet, and m dot v plus d of m dot v is the linear momentum at outlet. So outlet minus inlet will form d of m dot. Point is clear? Now one important part is left, that is to identify the forces. Okay. So what are the forces which we will be having? We will be having surface forces plus body forces. So if you talk about surface forces, we have two. One is pressure, other is viscous. I have already considered the situation of a frictionless flow, so viscous force is 0. Okay, body force will be coming because of the weight of the fluid. So can you tell me what is the weight of the fluid? So weight of the fluid will be rho g times dV bar, but we have to consider the component of this weight which is acting in direction of streamline. Okay, so component of this will be along this. So along this I will be finding a sine component. So force because of weight, please tell me, are you understanding or not? Force because of gravity is equal to rho g into dV bar sine theta. Okay, why sine? Because I have to consider the forces along the streamline. I am applying my RTT along the streamline. Point is clear? Okay, so ultimately what I will be getting? Rho g, in place of dV I can write it nearly equal to A into ds sine theta. And what is ds sine theta? ds sine theta is equal to dz. So it will be becoming rho g times dz. Fine. Rho g times dz. Is there anything wrong? Sorry, into A. Yes, rho g A into dz. Then I have to consider the surface forces. So surface force is what will be only pressure force. So you can see this is my stream tube. This is my stream tube. So over this stream tube I will be having some pressure P acting at this point, and then at this face pressure will be P, and at this face it will be P plus dP. So I will be having linear variation of pressure, and here pressure will be P plus dP. Once again here from P to P plus dP. So this is my distribution of pressure. So you can see that P term is coming common in all the directions. So if P is coming common, if I subtract the P term out of this, then ultimately what I will be getting? First tell me who has not got this pressure distribution, whatever I have drawn. Anyone is having any doubt in this? So at this point pressure is P, at the other end pressure is P plus dP. Okay, and considering the linear variation of pressure with the elevation, so I can draw a linear profile. So that's why this particular inlet face is subjected to total pressure P, considering the one dimensional uniformity assumption, and this entire is at pressure of P plus dP. Now this vertical face, this end will be at P plus dP, and this will be at P, and in between we will be having linear variation. Okay. Now what I will be doing in this pressure distribution, I will be subtracting over here the component P. Once I subtract this P component, what I will be getting? Quickly tell me. Here it will be 0, and this will be from 0 to, what will be pressure at this point? Please tell me. What will be pressure at this end? So this pressure will be dP simply. So this will be my new pressure distribution, dP. Okay. So what will be the force because of the pressure now? So dF because of pressure will be minus dP times, this is acting at the area A plus dA. Okay. And this particular uniformly varying pressure, this will be having average value of half of dP. Okay, so this pressure which is linearly varying, its average value will be half of dP, because one end is 0, other end is dP, and it is linearly varying. So average pressure will be half of dP, so plus half of dP, and this half of dP contribution whenever I will be taking in the streamline direction, this direction, then I will be getting that projected area in this direction is what? This is my projected area. This is my projected area. So what is projected area? in the streamline direction? dA. Have you understood this point? So this inner tube is having projection A and this extended portion is having area A plus dA. Okay. So projected area on which the pressure force is acting along the streamline, that is nothing but this hashed portion. This point is clear. So that's why half dP is the average pressure and it is acting on a projected area of dA along the streamline. So that's why I am using this half of dP into dA. Now considering only the first order terms in my pressure terms, if I neglect the second order term, then dP into dA will be very small, it will be 0, and dP into dA will be also very small. So ultimately I can write pressure force is nothing but nearly equal to minus dP times A. Okay, neglecting the second order terms, pressure force is nearly equal to minus dP times A. Okay, now let me substitute these into the main equation. So if I do substitute, what will be the sum of all the forces? One is pressure force, which is minus dP times A, or minus A into dP, and other will be the force because of the gravity, and this is also acting in opposite direction to the direction of streamline, so that is minus rho g A into dz. That will be equal to this del by del T of rho v into dv bar plus d of m dot v. Okay. So now we will stop at this equation and we will try to see how we can further put certain simplifications in this equation to get our final form, which is nothing but a Bernoulli equation. Okay. So the idea of using these assumptions and these complete derivations is so that you can understand at each and every time what are the different assumptions which we are invoking in deriving the different final equations. Because if we do the complete derivation, then only you will be able to understand the reason of applicability of these equations for different flow situations. Okay.